So today we're going to be talking about all things combustion and explosion related. We're on the chemistry side of things, even though this little meme points out um, the physical evidence of arson. We'll get to that in future lectures. Today we're just talking about the actual burning of substances. So we're going to be talking about the chemistry of combustion. Of course, that would include the evidence that you get related to arson, and then explosives all the way up through small explosives up through the largest explosions that we've seen in history of nuclear explosions. So combustion evidence is the second most common forensic analysis. So whenever there's a fire, and there's a lot of fires, fire departments are very busy, and they come and they collect evidence, and so that evidence comes in to the forensic crime lab, and you've got to find a way to see if there was any indicators of arson. So we're going to get into that a little bit today. We're going to talk about combustion basics and fires, and then this transition from combustion to explosion, because they have the same general properties, but there's a specific progression from a combustion to an explosion. And sometimes combustion can turn into vigorous burning, which then can convert into an explosion. And then detonation, there's sort of a different definition of detonation versus a deflagration or a vigorous burning. And then we get into the basics of explosives and the explosive train that you can take up as far as we can go in terms of our historical science, all the way up to a fusion reaction. So we can do fusion, we just can't control it at this point. I mean, they've done fusion experiments that have lasted up to minutes, but still, we're just right on the edge of being able to control fusion. So in terms of burning, we have this concept of the fire triangle, and we're surrounded by things that could burn. We're wearing things that can burn. Our bodies can burn. So what keeps us from bursting into flames just by being surrounded by oxygen? And there's a lot of oxygen in the air, and even more in hospitals. You've got all these oxygen lines that are spraying concentrated oxygen into the room. Things are more flammable in hospital environments, especially when the oxygen's turned up. People that are on oxygen are not supposed to smoke because they're blowing pure oxygen into their face, and sometimes that oxygen tube has caught fire because it's surrounded by oxygen. So what happens is you have this activation energy. So this is what actually protects us, this right here. And so we have this lot of things that can react with oxygen, but they don't react with oxygen because of this activation energy. There's something that needs to get it started, some sort of initiating event. But you have to have these three things: heat, fuel, and oxidant. So the heat is that activation energy. Once you get something started and getting over that hill, then if it's exothermic, it's what we call autocatalytic. So we need heat to get started, but this exothermic reaction feeds back into the reactants and helps get them over the hill. And so it generates more heat, gets more reactants over the hill, generates more heat, gets more reactants over the hill. So that's what gets a reaction started. And then this contact, you have to have mixing. And so if you don't have mixing, then you can stop this fire triangle. But you have those three things plus mixing. And so for firefighting, we can spray water mist on a fire to try to steal enough heat. And if you look up here, you see these little sockets, the tiny ones, not the speakers, but these sockets, those are sprinkler heads. And so if there was a fire in this building and the fire reached up, and I don't know that we have smoke detectors, but these sprinkler heads have a little meltable plastic piece that keeps the valve shut. And so if it gets hot enough, it'll melt that plastic piece, then the valve pops open, and then it starts spraying to try to steal the heat. Okay. Another firefighting thing is the CO2 powder. You know, it can have a chemical effect, and it can flood those reactants and make them not flammable. It can separate the fuel from the oxidant as well, because CO2 is denser than air, heavier than oxygen. And so if you spray a CO2 canister on there, or you spray a powder like bicarbonate that's going to generate CO2 when it heats up, then it separates the oxygen. So you have fuel surrounded by CO2, and it can't burn because you've unmixed the fuel and the oxygen. You've broken that fire triangle. And then foam also steals the heat and separates the fuel from the oxidant. And then halogens, they steal the heat. It's a chemical effect. And so halogenated solvents are a way to fight fire. Now it's dangerous because it produces a lot of acid gases. So if you throw carbon tetrachloride on a fire, you'll put the fire out, but you'll generate a lot of corrosive chlorinated gases, and so then that's a danger to the people in the room. So, but they do. This is an old way of fighting fires, and I was in the pharmacy museum at Texas Tech, and I took this photo here of a carbon tetrachloride extinguishing grenade. It's a glass container that has carbon tetrachloride in it. And so if there was a fire, say in the corner of the room, you would take this off the wall and you throw it at the fire. And that carbon tetrachloride would mix with the fuel and steal the heat of combustion. And hopefully there was enough there. If you hit the fire early enough, it'll put it out. And so that's a fire grenade. So I thought that was an interesting thing. So let's talk now about this idea of burning and how it differs from an explosion. So over on the left, we have what consists of, or what describes burning. You have a flame. Vigorous burning would be a deflagration. I'm trying to think if you guys have ever seen a deflagration. Most of our things that we see are burning. What's the most vigorous flame you've ever seen? Maybe a oxyacetylene torch. You ever seen anybody cutting steel with an oxyacetylene torch? When they add the extra oxygen, the iron is actually burning with the oxygen. And you hear a lot of sound when they do that. Yeah, there's that sound from the oxygen coming out, but when you start cutting that metal, you hear more sound coming from that reaction. That's a pretty common, I would say that's close to deflagration. It's just a really out of control, super fast burning, but it's still a burning. Um, and the and of course you have things like hydrocarbons. You could have metals too that burn. The oxidant is air. Here's the thing too, the pressure is low because it's unconfined. So burning and deflagration have low pressures. It's a thermal process. So it's that heat fire triangle. It's the oxygen and the fuel that are in a lot of heat, and they're burning vigorously. And then what how does that differ from a detonation or an explosion? Okay. The main thing that you could say is that it's this speed of the burning. So the burning, even if it's a deflagration, it's subsonic. So it's generating a lot of noise if it's a deflagration, but still the shock wave or the path of the energy going through that material is subsonic. Now, when we talk about sonic, we're talking about the speed of sound in the material. So not the speed of sound in air, but the speed of sound in the material. If that shock wave moves faster than the speed of sound in the material, then it's a detonation. So what does that even mean? Well, think about this, how sound is transmitted. My vocal cords are vibrating, and it's vibrating the air, and it's transmitting through the air to your ears at the speed of sound. Okay, how does it do that? Collisions. So intermolecular collisions. So the molecules are banging into each other through the air. Well, down in the solid, the molecules are closer together, so the speed of sound is faster in a solid. But it's still molecules colliding with molecules. That's a certain speed because the molecules have a certain mass, they have a certain intermolecular attraction. There's a speed of sound through all these different materials. If the energetic shock wave goes faster than that, it's moving through the material faster than the molecules can bang into each other, which is a little hard to conceive of. How does a shock wave go through a material faster than the molecules can hit each other? What's the other thing that can move faster than translating molecules? Light, right? Energy from that. So if the burning is confined and it gets energetic enough that it generates sort of an energy shock wave, light, both infrared, visible, and so on. All of these light, all the light, the radiative energy coming from that burning, if it transmits through the material in a way that's faster than the speed of sound, you move from burning to detonation. So what is characteristic of a detonation? The shock wave goes through the material and essentially breaks all the covalent bonds in the material. So think about that. Now all your atoms are that close to each other, and they can rearrange their bonding however they want. So if you have a CH2, those two H's and an oxygen are right next to each other in an explosive, and now those two covalent bonds between the CH are broken, and the water can form bonds with oxygen instantaneously. And it's exothermic. So you have water molecules next to carbon, maybe next to oxygen. So you have a CO2 molecule and a water molecule extremely close to each other. They're extremely high temperature, extremely low volume. So they want to expand. So that's why you get this explosion. So the shock wave moves through the material faster than the speed of sound. All the covalent bonds are broken. You have instant rearrangement. You have nitrogens that form nitrogen triple bonds. So you have nitrogen gas. You have water, steam. You have CO2, gas, all within the package of a solid. The solids are 1,000 times more dense. They take up 1,000th of the volume of a gas. And so it just at room temperature, they would expand 1,000 times. You add to that the temperature of the burning, and now it's maybe 20,000 or 30,000 or 50,000 times. So that's where the explosion happens. You have energetic breaking of the bonds, rearrangement to more favorable molecules thermodynamically, and then the heat and the expansion is what causes the destruction. Okay, so that's a detonation. But it's all about this speed of burn. Does it rapidly accelerate? And that's what that DDT stands for, the deflagration to detonation transition. Deflagration to detonation transition. DDT. So let's go back to slow burning, like the combustion of wood. This is what's happening when you have a yellow flame. I used to think it was sodium because sodium was yellow, and then I did some looking into it, and it's the hot carbon soot. So it's a black body radiator. So you could look at the light coming off of that orange flame and kind of get a feel for how hot that flame is. Okay. So that's the hot carbon soot. The blue flame is where the redox reactions are happening. So the heat is being radiated back to the wood, causing decomposition. And then the gases are coming out. Things like CH2 and CHO and all of these different fragments are coming off, and they're reacting with oxygen. And those are redox reactions. They're coming in and they're tearing apart those little carbon fragments and creating heat that further decomposes the wood, which generates more fragments, which generates more redox reactions. So we can use the enthalpy of combustion as an approximation of the amount of heat that's released. And so this is the latest research. I added this yesterday and re-uploaded the notes. This is a paper that Tommy Gilpin, my grad student, and Victoria White, who's a former undergrad, who's now working at Huntsman, she helped write this paper too. So there's 3 authors on this paper, and we're submitting it to the Journal of Engineering and Chemistry Research. And this is a very simple little model. We took 1,000 compounds out of the CRC, and we basically did a regression analysis of A, B, C, and D, the number of atoms of carbon, hydrogen, oxygen, and nitrogen in this reaction, and we modeled the enthalpy of combustion. And it's the lower heating value because we still have gaseous water. If it was the standard enthalpy of combustion, we would have water at room temperature, which would be a liquid. But we don't always capture that heat. Water escapes as a gas and turns to a liquid somewhere up in the upper atmosphere. So it gives off heat when it becomes a liquid in the cloud, but we don't capture that in the room or at the match head or in our combustion engine. So the lower heating value is a more accurate number to use to determine how much heat comes out of a substance when it burns. It's not a perfect model because we can't tell the difference between, say, ethanol and dimethyl ether. They have the same chemical formula, but they have different structure. Okay, so we only get about 85% of our results are within plus or minus 10% of literature. So it's a pretty good model. The other 15% of those results are isomers, and so our value is getting the average isomer value, and you'll have some like amino acids will be low, and nitro alkanes will be high, and they'll have the same molecular formula. But look at the result of this equation, this right here. So use this equation on your homework, and you can generate the enthalpy of combustion by knowing the number of carbon atoms, the number of hydrogen atoms, the number of nitrogen atoms, and the number of oxygen atoms. That's pretty handy, and that's what we wanted to do. That's why we want to publish it, because it's something that you can use with a calculator. It's no different than calculating the molar mass, right? If I have 3 carbons, I'm going to multiply that by 12.01, and if 5 hydrogens, I'm going to go up and multiply that by 1.008. And this is the same kind of equation, only this gives you the heat of that molecule reacting with oxygen. So that's how much of the enthalpy, the lower heating value, comes out of these organic molecules. And we get a pretty good R squared, 0.9986. You can see the scatter down here is due to those isomers. So our value would give one number for all of these values here. And some of those isomers, like I think it was heptane, think of all the ways you can make heptane, right? You can move, and then it can be, 2-methylhexane, right? Or then you could have a butyl pentane or something like that. So you could move those different branchings and so on. So there were 26 isomers of heptane in our model. We get one value for that with our model, and literature has 26 values. And so there's a fair bit of scatter. Now there's not a lot of difference between all of those, moving the methyls around, and so it's still pretty good for those numbers, but still we don't model isomers. We're just going with the number of types of atoms. So let's talk about specific heat of combustion. This may be better, say if you're a fire chief and you're inspecting this building. When I was at Pantex, I constantly got dinged by the fire inspector because they would come along and look at my office, and they would look at it and estimate the amount of weight of paper I had in my office. Okay, and I had filing cabinets full of paper, and I had one little sprinkler head in my office. And so they're saying this sprinkler head can handle so many joules, per second. It's spraying out the water, and it can keep the fire in this little space until the fire department comes and gets it put out. And that's the goal of all of these sprinkler heads. If it can put out the fire, great, but its main function is to contain the fire to this room while the fire department comes. And then they bust open the window or come in the door, and then they can put it out. Okay, but we don't want there to be just so much fuel in this room that it breaks through the door. And many of the doors are like 2-hour doors. So the sprinkler head and the door will keep it in this room for 2 hours. And then hopefully the fire department can come in that amount of time. I had so much paper in my office, the fire marshal was saying, you got to get rid of some of these filing cabinets. We need to archive some of this stuff or shred it or get rid of it because you have more combustible load in your office than the sprinkler head can control. Okay, and he was doing that using the specific heat of combustion. So this is the heat generated by a certain mass of substance, and so this right here is our previous equation that we just showed. That's the enthalpy of combustion on top, and the molar mass on bottom. And the top was kilojoules per mole, and the bottom is grams per mole. And so this gives us kilojoules per gram. And notice up here, these are the hydrocarbons. And so the smaller hydrocarbons are pretty high, like methane is 50. This is methane, CH4. But then you get to the bigger polymers and stuff like that, some of the heavier molecules. This tops out at around 42 kilojoules per gram. So that's the sort of the average value for your hydrocarbons. Then you have oxygenated substances, substances with nitrogen, and so on. And so when you have these branches here, this would be like um, alcohols, acids, and so on. As we add oxygen and nitrogen, we're adding mass, but we're not adding a lot of things that give a lot of heat. And in fact, this is the oxygen number. If we add oxygen to our organic molecules, they're already partially reacted. And so oxygen has a negative coefficient. So it doesn't make any sense to put ethanol in our fuel. We're putting something that's already partially burned in our fuel. So there must be other reasons for adding ethanol to our fuel. It's not because you get more energy out of it. So here's the delta H mass, the specific heat of combustion. And this is how well our model works against accepted values. So for coal, if we model coal just as carbon, we get 35.9 kilojoules per gram. And for anthracite, high quality coal, that's pretty consistent, okay? Natural gas, we model at 49. The accepted value is 48. Crude oil, it's about 88% carbon and 12% hydrogen. And so we get good numbers there. We can do non-carbon fuels if they have, nitrogen and hydrogen. We have that in our equation. And so ammonia is pretty close to its accepted value. Methanol is about, 15% low. It's a little over 10% low. But still, it's in the same ballpark. Gasoline, if we model gasoline as octane, we get comparable numbers. Diesel, if we make a bigger molecule for diesel, we get a comparable number. And look what happens when we add an oxygen to our organic molecule. Compare that to gasoline. So 44 for octane, 26 kilojoules per gram of ethanol. So that stinks. We're taking away a lot of the thermodynamic power of that molecule by already reacting it with oxygen and then trying to use it as fuel. We could do nutrition with this. So the average sort of an accepted molecular formula for protein in the nutrition texts gives us this formula here, and our value, our model computes 24 kilojoules per gram, and that's within the accepted range of protein in a diet. Same with fat. If we model fat with these stearates, then we get 37.5 kilojoules per gram, and that's within the range of accepted values for fat. And carbohydrates, 14.9. It's a little bit lower than the accepted value, but it's still in the ballpark. We could use fire suppression numbers too. So this is a freon. Notice it's all fluorinated and brominated, and we get a negative number. It's not the same magnitude as the accepted value, but it is showing that it's an endothermic reaction. It steals the heat from the burning. And then combustible loading. So this is what that fire engineer was doing in my office. He was estimating the amount of mass of paper and combustible wood in my desk and everything else in my office, and coming up with a number. And this is the accepted range for this. And our cellulosic material, if we model it with C6H10O5, we get 16.5 kilojoules per gram. But I don't buy my ethanol or my gasoline by the pound. What does the gas pump do? It does volume. So we also did a regression analysis on molar volumes. So if I have more atoms, I'm going to have more volume for that molecule. And again, we get comparable results. 87% of our results are within plus or minus 10% of the literature value. And so here's your molar volume equation. So just like the last one, if you know the number of carbon atoms, hydrogen, nitrogen, and oxygen, you can calculate the molar volume. If you take the ratio of the heat by the molar volume, you're going to get the volumetric energy density. So here's the volumetric energy density. You have the heat equation on top, which is kilojoules per mole, and our molar volume are mils per mole. And so the moles cancel, and we end up with kilojoules per milliliter. So this is the amount of energy in a volume of liquid. This is helpful at the gas pump, right? I'm buying volumes. And sure enough, the hydrocarbons are the highest ones. There are some oxygenated compounds that are pretty high up here. Um, there's some nitrogen compounds that are up there too, um, but the hydrocarbons do the best. And notice that oxygen hurts you here, um, and oxygen adds quite a bit of volume, so it's increasing the denominator and decreasing the numerator, and so oxygen is bad to have in a fuel if you could avoid it. Now, how does that fit with these guys that have hot rods and they want to get a boost? They put nitrous oxide in their tank, or in their fuel line. They have a nitrous boost. What's going on with that? Well, that's just adding oxygen to burn with the fuel. So with that, they're adding a lot of fuel, but they're also throwing in nitrous oxide. So they're not adding in nitrous oxide as a fuel, they're adding it in as an oxidant. So if they just stuff air in there, only 20% of the air is oxygen. If they stuff in nitrous oxide, it's like 67% oxygen. So it's twice, 3 times as much oxygen if they're spraying in nitrous oxide than if they're just stuffing in air, say with a turbo. So our volumetric energy density also works well as an estimate of fuel performance. So for gasoline, we get 31.8 from our model, and the accepted value is 32.4. We're within the range of diesel or slightly below it, but close. And then here's the E15 gasoline that you see at the pump, which only has 15% ethanol by volume. But look what happened to that formulation. It's lower than the gasoline. It's much lower if you have E85. Now, if you look at the price of E85, it's lower, and you might be tempted. You're like, well, it's cheaper. Well, it's cheaper because you're going to have to fill up. You're going to have to fill up more frequently. You're going to get less miles per gallon because there's less energy in there. The reason you're getting miles from the gallon is because of the energy of that combustion. And so if you have less energy of combustion, you have to push on the pedal harder. You have to put more fuel in the deal, and you run out of it faster. And so that's why E85 is cheaper. It's not necessarily cheaper to make. You're going to have to fill up more frequently. Okay, it doesn't take you as far, so it's just not as valuable. Okay, so these are the tools of the trade. When you're looking at this enthalpy of combustion, you're looking at the heat that's generated. You have that mass of fuel, you have the enthalpy of combustion, and we assume that there's no time for heat to escape. So we're trying to harvest all of that heat. You get large forces. This is what I was talking about, the mass of the number of moles of gas. So you've got, the CO2 and the water, gaseous water, and that produces a large force that pushes on the walls, pushes, on the air and so on. And then you have this stoichiometric ratio, the mass of the fuel to the mass of the oxygen. And so this is a mass over mass. So this will be a percent composition that's perfect. Or no, this is the actual right here, the system that you have. And the stoichiometric amount is the perfect amount. And so this stoichiometric ratio, phi equal 1, is dangerous. Because if you have a situation, let's say you have a gas leak in your house and it's mixing with oxygen from the air, and you have the stoichiometric amount, it's ready to go. One little activation energy and that whole house blows up. Okay? So the only thing keeping that from blowing up is that activation energy. Everything else is there, it's well mixed, and you've got a dangerous situation. So what is the stoichiometric equivalent for methane in air? Let's walk through this. So the moles, the number of moles of fuel to oxygen is 1 mole of methane to 2 moles of oxygen. So you can see that this is our balanced chemical equation. And so the stoichiometric amount in terms of moles is 1 to 2. But in the way that fire safety engineers and so on they think of masses. And so let's convert this to masses. So what's the mass ratio of fuel to oxygen or fuel to air? So how many moles of air will produce 2 moles of oxygen? Okay, we need to know the atmospheric composition. So you can get this, you can just Google this. This gives you the major components of air. It's 78% nitrogen, 21% oxygen, about 1% argon, and a few parts per million of CO2. So we can ignore CO2. Many times we just ignore argon too and say it's 20% oxygen and 80% nitrogen. But let's be more specific this morning. So we've got 2 moles of oxygen that we need, and there's 0.209 moles of oxygen per 1 mole of air. And so we need 9.57 moles of air. Well, what's the mass of a mole of air? Okay, so 1 mole of air is 0.781, so 78.1% times the molar mass of nitrogen, 0.209 times the molar mass of oxygen, 0.009 times the molar mass of argon. So we end up with this, 28.9 grams of air per mole. So you could put that, I'll put that on the equation sheet for you guys, okay? But I'm just showing you where that number came from. And so how many grams of air would give us the 9.57 moles? This would be 277 grams of air. And then for our methane, we needed one mole of methane. That's 16 grams of methane over 277 grams of air. So that's the mass percentage of the stoichiometric amount. The perfect amount of methane in air would be 6%, 5.8%. So that's the danger zone. Because that's the perfect amount of methane in air. If you were to let this methane gas go long enough for it to reach 6% in this room, we would have to be very careful. You're like, oh, I got to get my laptop out of there, and I pull the plug, and there's a little spark. Yeah, not good. Okay. And yes, you need to be able to do these kinds of calculations. So come back to this video and walk through it. So let's do an example calculation. Would a 5 liter per minute gas leak reach an explosive concentration overnight? So 8 hours. We're going to have to make lots of assumptions, but these are the kinds of assumptions that we would make, okay? So 5 liters per minute, we've got 8 hours, so we know how much gas is going to be there. So let's start with the 8 hours to get the mass of fuel that comes out. So how can we get to the amount of natural gas coming out of this thing in 8 hours? Well, we start with 8 hours, and we've got a liters per minute, so let's convert those hours to minutes. We got 60 minutes per hour. And we just let our units guide us. So then there's 5 liters per minute of that leak. And so then what's the number of moles per liter at 1 atmosphere and room temperature? So this would be the ideal gas law. V equals nRT over P. So we got 1 atmosphere, 298 Kelvin, the ideal gas constant. So in this case, R is equal to 0.08206 liters atmospheres per mole Kelvin. And then to get from moles of methane to mass of methane, we use the molar mass. So that's 12 plus 4, gives us 16. And then we have a lot, because we have all our numbers on top except for this 24.4. So we're going to just go ahead and convert it to kilograms. And we end up with 1.57 kilograms of methane. So that's how much methane we have in this house. What about the mass of oxygen in this house? Well, we need to know something about the house. So let's just pick a, um, I don't know, an average house with 8-foot ceilings. Say 2,000 square foot house. Again, houses vary quite a bit. So this is just the assumption that I made. You might be in an apartment 600 square feet. Okay. And then we've got feet to liters. And then from liters to air, that's the ideal gas law again. So we've got 1 mole of air here, 24.4 liters. Then we got the molar mass of air. We want to get out of moles of air and into mass. We just did that on the previous page. Kilograms to or grams to kilograms. And we end up with 536 kilograms of air. So that's how much air we have. So this ratio MF over MO would be our actual, or our sys, our system. So this 1.57 kilograms of methane to 536 kilograms of air would give us this system ratio, the sys. It's 0.00239 or 293 kilograms of methane per kilogram of air. So our phi would be 0.05. And so, no, it's too lean. Even an 8-hour leak at 5 liters per minute is too lean for it to have an explosive atmosphere in our house. So if we were at a phi of 1, it would be explosive. Um, and a phi of about 0.1 would be maybe the lower explosivity limit, and a phi of 1.1 would be the higher, the upper limit. You could be too rich too. If this phi came out at 2.0, you'd have twice as much fuel as you need, and then you don't have enough oxygen. And so it's still dangerous, but it's not dangerous because of the amount of methane in the room. It's dangerous because somewhere between having a phi of 2 and the hallway where you got a phi of like, you know, 0.1 or something, it goes through 1. So going from a phi of 2 to a phi of 0, you're going to have to pass through a phi of 1, which would be an explosive range. So they have explosive gas monitors in the fire department. Somebody smells a smell in a warehouse, and it's scary to them. Maybe there's some smoke and so on. They walk into that warehouse with the little gas monitor, and they're measuring this phi. They're measuring, what percent of the explosive vapors do I have in this room? And if they go in and phi is much greater than 1, they stop and they start backing out carefully because they're going to go through an explosive zone on their way out, and they don't want anything to happen. They need to ventilate and get air in there to get it to go away, get those explosive gases to go away. Now, this would be if everything's perfectly mixed, but notice that air is 28.9 grams per mole and methane is 16 grams per mole. So if the room is still and there's no ceiling fans or anything like that, what do you think is going to happen? What will the methane do? If it weighs 16 grams per mole and air is 28 grams per mole and the room is still, there'll be layers. So it'll stratify. The lighter gases will go to the ceiling. And so you might have an explosive atmosphere at the ceiling and not down at the floor. If you have, say, you're refinishing something, trying to strip the paint off something, and you're using gasoline, and you got a big gallon jug of gasoline, and you put your parts in there, and it's open, where's that gasoline going to go? It's going to flow down, and they're going to have gas vapors along the floor. So you might not come in, you might smell a hint of gasoline, but along the floor, you've got an explosive atmosphere of gasoline. That can be a problem in the garage. So, so this is what's going on. The lower and upper explosion limits. Okay, this says we're safe at 0.25. I said 0.1. So 0.25 is too lean. If it was 1.25 would be too rich. Here in the middle, you've got the danger zone. And so on an SDS, a safety data sheet, you'll see for different substances an LEL and a UEL listed many times. And those are those stoichiometric ranges that you want to stay away from, or those relative, the phi values you want to stay away from. And you can see for methane, like if you have a stove that's leaking, it's going to concentrate around the ceiling. It's going to be too rich, very high, but there'll be a hugely flammable region, maybe an explosively concentrated region. Now let's switch gears. We've been talking about burning. Now let's talk about explosives. So when I'm cooking on my cook stove, I'm just pumping fuel out into the air, and the air is providing the oxygen. Okay, that makes sense. When I in a high performance drag race car, I'm going to put in nitrous oxide. So I'm throwing my fuel in there, and I'm throwing in oxygen as a separate molecule, and I'm trying to tune those, and so I'm adding the oxidant, but it's still a separate molecule. Maybe if I'm driving a diesel truck and you hear that whine of the turbo, what's that do? You hear it. The exhaust gas is spinning a turbine, which then is spinning another turbine to suck air in and stuff it into the cylinders. So again, I'm still adding oxygen with the turbine to more completely combust the diesel energy. But the diesel fuel is the diesel fuel. It's a hydrocarbon. And the air from the turbine is just stuffing more air. It's still only 20% oxygen, but I have a higher pressure of that oxygen, so I get more combustion. What if we took the oxygen and reacted it with the organic molecule and put it in the actual molecule? So in the molecule itself, it has the oxygen for combustion. So these would be functional groups that are still pretty high energy, like a nitro group. So if we put nitro groups on an organic molecule, the oxygen and the nitrogen are not double bonded. I mean, there's like a resonance structure where you might have a double bond to one oxygen and a single bond to the other, but wouldn't it be better if you could just take those oxygens and stick them on a carbon atom and make double bonds to both oxygens? You see how that would be better? So let's put oxygen in an organic molecule, but let's have it stuck to nitrogen. And then if we get a shock wave through this material, the oxygens will hop to the carbons and release a lot of energy. The oxygens will also strip all the hydrogens off the molecule and make water and release a lot of energy. And then the nitrogens will find other nitrogens and make a triple bond, and that will release a lot of energy. So this is a way to get the most chemical energy out of a substance, and everything's in the molecule itself. So I've just taught you how to make an explosive. You've got to take the oxygen and get it in the molecule itself, but in a form that it doesn't really want to be in. It wants to be connected to carbon. It wants to be connected to hydrogen. We're going to connect it to nitrogen, and we're going to stick it in the molecule. And then the nitrogen doesn't really want to be connected to oxygen. It wants to be connected to other nitrogens. And how do we get that nitrogen free to make a triple bond with other nitrogens? We need a shock wave to come through and break all those covalent bonds. So we can make explosives that are quite stable. I mean, you can machine them. You can stick them in a lathe or a mill, and you can cut them to shape. They're engineered substances, and that's not enough energy to create this detonation wave. So this is how we make safe explosives. So this is when oxygen is used as part of the molecule. Notice where oxygen is. It's in the molecule. Notice there's no plus O2 in this reaction. This isn't combustion. Combustion is fuel plus O2. There's no plus O2 as a reactant. This is a decomposition. This molecule is becoming a bunch of other molecules and releasing energy. It requires activation. There's an activation energy, but once that happens, this molecule can release all of its energy at once. So this is the ideal reaction for carbon, hydrogen, and nitrogen. And so we're going to form O2 as a product. we're going to form nitrogen into as a product, water as a product, and CO2 as a product. And so let's take nitroglycerin. This is what nitroglycerin produces. And what we want to see is we're going to leave this O2 as a question mark. And we want to calculate the amount of O2. If this is a negative number, because notice we have the oxygen in the molecule, but we have to subtract the oxygen that went to the CO2, and we have to subtract the oxygen that went to the water. And if there's any oxygen left over, then we'll have oxygen come out of the system. But sometimes these organic explosives don't have enough oxygen, and we would say that they have a low oxygen balance. So let's do nitroglycerin. So let's calculate what our oxygen coefficient is. So it's this 9 here, 9 moles, goes into the D. We have the 3 for the A, and we have 5 for the B. And so we put in all of those, and we end up with 0.25 moles of oxygen left over after nitroglycerin makes CO2 and water and nitrogen gas. It has a little extra oxygen that comes out of it. So we call that's a positive oxygen balance. Typically, things that have a positive oxygen balance are more sensitive. Like nitroglycerin, if you tap on it or agitate it, it's shock sensitive. So you shock it mechanically, not electrically. That's spark or static. Shock sensitivity means you hit it with something. You hit it with a hammer. What do all of our firearms do? They have a hammer. You pull the trigger, the hammer hits a shock sensitive explosive that then starts to detonate. And so our oxygen balance is this 0.25 moles of oxygen times the 32 grams of oxygen per mole. So we get rid of those moles. And so if they have that many grams of oxygen over the grams of the molecule, so the mass of nitroglycerin. And so we end up with it's plus 4%. So it's 4% high. And we know you've heard of nitroglycerin. You know it's an explosive, a shock explosive. Okay, what about TNT? Everybody's heard of TNT, trinitrotoluene. We take toluene and we put 3 nitro groups on it. It's really tricky synthesis because it's it's endothermic to get the first nitrogen on. Let's see. Yes. Yeah, it's endothermic to get the first nitrogen on and exothermic to get the second and third nitrogen. And so once you get the first one on, the second one hops on and then generates heat to get the first one on the next molecule, and so the reaction rate speeds up. And so that's why it's so tricky. We don't have a lot of people making TNT at their house, thank goodness, because a lot of times they blow themselves up trying to do it. This organic synthesis, you got to keep it in an ice bath. You got to go slowly because it's going to accelerate once you get it started. And so here we do the oxygen moles. We have, again, 7 carbons and 5 hydrogens and 6 oxygens, and we end up with a negative number here. Okay, we convert that to mass and divide by the mass of TNT, and we end up with negative 74%. So there's not enough oxygen in trinitrotoluene to react with all of those carbons. So where do we get the oxygen? We don't have enough time for air to provide the oxygen. This is instantaneous detonation. Well, not really instantaneous, but it's faster than the speed of sound, which means air has no time to get in there. So what happens to this molecule? Well, it produces a lot of carbon. So since we don't have enough oxygen, we end up with just soot. We have carbon soot or incomplete combustion. But so this shows you that TNT is not as efficient as we'd like. We could get more power out of this molecule if we could get more oxygen. So this is where explosive engineers say, oh, let's juice up TNT a little bit. Let's maybe add a little bit of nitroglycerin to TNT. And nitroglycin's going to produce 4% extra oxygen, and that will help combust the carbon in TNT. That would work because they're both solids. Well, liquid nitroglycerin in a solid TNT. You could put a certain amount in there and it would remain a solid. Maybe you could combine it with a polymer that had a lot of oxygen. And so you mix the TNT in with a polymer or maybe a plasticizer that has a lot of oxygen. And so there's ways explosive engineers work with, and that's where you get all these formulations like C4 and Semtex and all of these different kinds of engineered explosives. They're not just pure TNT, they're engineered with the properties that they want them to have. Now we'll go back to burning. We've got this heating curve, and you can see what's going on. This is just a simple candle. You've got the wax that's melted, so this melting point has a particular temperature associated with it, and that is not very hot. Many of these substances, compared to burning, are actually hampered by melting and then vaporization at the boiling point. So you get this temperature bath effect if you have a bulk fuel, because you've got to evaporate the fuel or melt the fuel for it to burn. And so this is what we see, and we're going to get into the physical evidence in the future, but this right here is such a weird phenomenon, this donut burning pattern. If you pour gasoline on the carpet and light it on fire, the heat from the gasoline fire will eventually degrade the carpet, and this went down to the flooring here, but you can see some of the gasoline spread out here to these carpet fibers and didn't burn. And then this area here was held temperature I'd say the boiling temperature of the fuel. So the boiling temperature of the fuel is pretty cold compared to the heat of the burning. And so that carpet in the middle is protected because it's soaked with fuel, and it will rise up to the boiling point of the fuel and never get any hotter as long as there's liquid fuel. And so you can see these donut burning patterns. If the fuel then all of a sudden it all boils away instantly and the flame goes out, then you would leave behind the little bit of carpet soaked in fuel. And that's like the thing you want as an arson investigator. You want to grab that little piece of carpet that's in the middle of that donut, get it into a metal can, an arson can, and seal the top, hammer it shut. It looks like a metal paint can. And you hammer that shut, and so you've captured the fuel that was used to start the fire. And so that's the chemical evidence that you're after. So the charring effect will tell you a lot about where the pattern of burning will tell you where the fire started. So a lot of times arson investigators can see this V, say on the wall where it's charred. And they go down, since heat rises, they go down and find the lowest point, and that's where the initiation of the fire began. So you see this charring effect. And so let's go back to this deflagration, charring, burning as it switches over to detonation. This is typically referred to as DDT, the deflagration to detonation transition. So when there's flames and so on, there's really no pressure buildup. But if you start to confine things, then you get built up pressure, and then you get a pop or an explosion. Did y'all ever play around with fireworks when you were a little kid? Maybe you still do. Okay. I used to break them open like black cats. I would break them open to where you could see the gunpowder in the middle, the black powder, and I would just light it with the punk, and it would fizz and sparkle like a fountain. So it turned a black cat, which pops, to a fountain, just because I broke the pressure buildup. There's a lot of paper there, and that paper holds it till the pressure builds up and the paper then bursts, and that's what makes the crack sound of a firecracker. Okay, if you break it open, that black powder just burns and it's not confined, and so you have deflagration then. it's actually not an explosion when you get that pop. It's just acting as a propellant, and you have a controlled pressure buildup, and it's made out of paper, and so paper can only hold a moderate amount of pressure before it pops. Okay, but that's what's happening. So gunpowder is really not an explosive. Even when it's put in a container, it's really not an explosive. It's a propellant, and then the container gives way, and that can cause what seems like an explosion. But it's not a high explosive. It doesn't have a very good oxygen balance, and it's just burning in there, deflagrating, and then you get a pop when the pressure vessel breaks. But you could take something like a fuse, something that's burning or a propellant, and you could put it in a controlled pressure buildup chamber, and then when it pops, maybe that shock is enough to set off a higher explosive, a chemical with a high oxygen balance. And so let's talk about this explosive train idea, how to turn a fuse into a detonation. That's what we mean by the train. Now there's different ways of making sensitive substance, or different sensitivities. We've been talking about shock sensitivity, like nitroglycerin. When you smack it, then that is enough to initiate the activation energy for this explosion to take place. But you can have other things that are heat sensitive, or friction initiated, or spark initiated. So these are different detonators that we use in our blasting caps. So you've probably thought of fuses, right? So you light this fuse, and it's crimped into this metal piece, and then you have this pyrotechnic ignition mix. Pyrotechnic is very similar to the like the fireworks that we have. It's like a black powder, or maybe some kind of perchlorate substance mixed with fuel. And so when the heat from the burning of the fuse decomposes the perchlorate and is mixed with the fuel, you get a vigorous burning, and it's confined. And so there's pressure buildup. And then you have a primary explosive that's sensitive, and it starts to detonate. And that's what makes it go from a deflagration to a detonation. You start to build up that energy release. You start to get a shock wave that goes through the material. And then you have this output explosive, which has a high oxygen balance and can really, really produce a heavy-duty shock wave. And so that's what's going on here. You start to build up that shock wave in the output explosive. And then you plug this detonator into the main charge. So you have see the explosive train, something that's easily ignitable, something that builds the pressure, something that converts it into a detonation, and then you take that detonation wave and you put it into a main charge. Now there's lots of ways to generate this initiation. You could use what we call an electric match. So this is something you put a low voltage current through, and it heats up and generates a flash. Or these are sort of industrial down here. So these are like the real ones. If you saw something like an exploding bridge wire or Kapton slapper explosive, that's something that's military or government of some sort. The ones above are, maybe some of these are government too, but these down here are high tech. And so these are the chemical explosives that we would deal with. These are primaries and low explosives. And this is the one that you're going to see the most of in gunshot residue, this lead stiffnate. And it's mixed with barium sulfate and antimony sulfate to generate, again, some more heat. And that's what's in the primer for store-bought ammunition. So it's in that little button that the firing pin hits, and that firing pin hits it and causes lead stiffnate to detonate. It starts to deflagrate, and then it starts to detonate, and it pushes the shock wave into the black powder, which generates a propellant gas that's going to propel the bullet through the chamber. Okay. You also have other things like lead azide, mercury fulminate. Sometimes these are mixed in to primers. Then you have nitroglycerin. Nitroglycerin is just too sensitive to use, so too touchy. You can manufacture it pretty easily. You take glycerin, which has got 3 alcohol units on it, and you react it with nitric acid and you can nitrate it. But then the product is so dangerous that it's not very functional, right? You can't carry it around. Certainly not going to be useful in a military uh, um, aspect because it's shock sensitive. Let's say you have a bunch of it in the back and somebody shoots a bullet into that container, then it all blows up. So that's not going to be good. So what they did, Alfred Nobel discovered that you could mix it with diatomaceous earth, which is a bunch of little skeletons of sea creatures and so on. It's like basically sand, but it's not the silicon part. It's the little sea creature part, diatomaceous earth, and it would not be shock sensitive anymore. And he gave it the name dynamite. So that's where the Nobel fortune came from, was making stable nitroglycerin for use in mining, and also got used in military affairs too. So he felt bad about that, and so then he set up this foundation to give the Nobel Prize for peace and science and so on. So that's kind of a backstory of Nobel. It was stabilizing nitroglycerin that made him so much money because it was useful in mining and also in military applications. Now, if you can react nitric acid with OH groups, like in glycerin, maybe cellulosic material, which has tons of OH groups, could be reacted. And sure enough, you can react nitric acid with cotton and other kinds of cellulosic materials, and you can make nitrocellulose. So that's what this is here. So you can see the cellulosic ring structure, and you see all of these ONOs. Those are the nitrate groups. And the more nitrates you put on there, the more flammable or propellant this gun cotton is. And they still use this in our artillery. So they have these little marshmallow-looking bags that are filled with nitrocellulose. It's very easy to control this synthesis, and so they know exactly how much pressure each one of those pillows is going to produce. So you shove the shell into the cannon, and then depending upon the distance, you put 3, 4, 5 little pillows of the nitrocellulose, and then you close the breech, screw in the screw, and then you can pull the detonator, and it will detonate the gun cotton. And it's not a detonation, an explosion. It's a propellant. It burns at a known, well-characterized rate and throws that shell for miles. Okay. And then you can take pentaerythritol, which is a carbon surrounded by 4 carbons that have alcohols on them, and you can nitrate that, and so you end up with this pentaerythritol tetranitrate. So there's only 4 nitrates. Where's the penta part? Well, it's 5 carbons, so that's where the penta part comes from. So PETN, probably the most common detonator explosive. And I'm going to call it sniffable. So you might have a big bomb in a suitcase, but it doesn't have a very high vapor pressure. But this tiny amount of pentaerythritol tetranitrate in the detonator has a high vapor pressure. And so your little explosive sensors at the airport and the dogs too will smell the PETN way before they smell the main charge in some cases. So TNT is not very volatile, but PETN is very volatile. Now for the main charges, the bulk explosives, you see things like trimethylene trinitramine, RDX, and tetramethylene tetranitramine, HMX. And so this has a special group here called a nitramine. Remember I said we want to get the oxygen attached to a nitrogen because it doesn't really want to be. Put that in the molecule, and then that oxygen can react with the carbons and the hydrogens to make water. And then the nitrogens need to find another nitrogen. This is perfect because you've already got a pair of nitrogens here. And so when the oxygens leave to go react with carbon and oxygen, I mean carbon and hydrogen, these nitrogens can form this triple bond and make nitrogen gas. So these two explosives are really, really efficient, and they give a lot of energy out. Then you have this one that has a kind of like TNT. Here's trinitrotoluene. So you've got nitro groups. Notice there's no nitrogen here. So this is a nitroaromatic. This is a nitramine. So I expect you to know the difference between those. So the nitramines have a nitro group stuck on a nitrogen. So that's a nitroamine, and this is just a nitroaromatic. Here's picric acid, trinitrophenol. So instead of toluene, it's got an OH group here. And again, 3 nitro groups. And then tetryl, this is a weird one because it's got 3 nitro groups. So it's a nitroaromatic and it's a nitramine. So it has both. It has a nitramine in the side group, and then it's 3 nitroaromatics. Now these are all nitros on this page, or nitramines. Look at the previous one. These were nitrates. So this is a tetranitrate. And an organic nitrate is an RONO2. So that's different than the nitramine and the aromatic nitro. So notice this nitrate has got 3 oxygens. It's like nitric acid, but you've taken off the hydrogen and stuck it on an organic molecule. Okay. So if we have the detonator and it goes into this booster and then it goes into the main charge, we're going to find chemical evidence right here because this shock wave in the detonator goes into the material, but it doesn't turn the corner very well. So this corner turning, this inability for the explosive to turn, shock wave to turn that corner, means you're going to have chemical residue left behind. And so you may think this was an explosion. How can there be any explosive left over? That's because the shock wave doesn't turn the corner very well. And so you always have residual explosive left behind. The trick is what substance is it going to be on? And so Dr. Monjardet, she does explosives in the forensics research area, and they swab, like they'll have a little toolbox, they'll put a explosive charge in there, they'll have a cell phone, they'll have duct tape, a bunch of different pieces of material in there. They'll blow up this little toolbox, and then they'll go swab everything, and they'll go to the microscope and look for crystals of the explosives and so on. And so they're finding explosive evidence after post-detonation or post-blast. Now, what if you took this main charge and you pushed uranium-235 together? So uranium-235 here. So you have a subcritical mass on the left and a subcritical mass on the right, and you squeeze them together until they made a critical mass. Then that's how a nuclear detonation is made. So that would be a fission reaction. Notice the uranium-235 is breaking into 2 parts, strontium and xenon. It can break into a bunch of different atoms. Anything that adds up to 92 protons, it can break into. Produces neutrons and gamma rays and so on. But this releases an enormous amount of energy, such that a pellet, this big right here of uranium-235 could power 1,000 homes for a year. I mean, it's an enormous amount of energy. We could release that in a short period of time, and that's what a nuclear detonation is. If you were to put tritium in the mix, then you can squeeze tritium together and fuse it and make helium. If you can make helium, then you release even more energy than you get from fission. And so this is that explosive train. You have an initiator that gets the thing started, whether it be spark, flame, or shock. Then it goes into an explosive, like a propellant, that starts to build up the pressure. And then eventually it turns from a deflagration into a detonation. the shock wave starts to go through the detonator and into the booster explosive, and the shock wave builds and builds and builds with a more efficient explosive. Then it generates an enormous amount of pressure that can push subcritical masses of fissile material together to make a nuclear detonation. And if you put in something that's fusible, like tritium, like lithium, like deuterium, to make helium, then you get fusion energy out of it. Now, that's comparably easy to do to make a destructive device like a bomb. Okay? The reason I'm telling you all this is because of the evidence, right? What is the chemical evidence you're going to find? You're going to find detonators, you're going to find things that are left over post-blast, but we hope we don't have to do a post-blast analysis. We'd like to do pre-blast analysis. The grenade or handmade grenade that they had up in this recent protest, I forget what city it was in, it was TATP, triacetone triperoxide, a homemade explosive. And it didn't go off, which I'm shocked because it's super sensitive. Anyway, they threw that. And so that would be, again, a chemical signature of a homemade explosive. And then once it blows up, it generates an enormous amount of power. This push power that it has can be a sharp peak or a slow peak. This would be the braking, and this would be the pushing. So if most explosives, high explosives, produce this kind of pressure curve, you get an enormous and quick release of energy and a lot of pressure. If you have a burning associated with it, like maybe a fuel bomb or something with aluminum powder in it or zinc powder, metal enhanced blast explosives, then you get this overpressure, and this is what knocks things down that are hard to knock down. So our modern engineered explosives, blast enhanced explosives, have this sort of high pressure, sharp peak, and then this overpressure that's a really slow overpressure that pushes things down. And then once it retreats, you get actually a vacuum. So it actually goes below ambient and pulls. And so you might hear it called a vacuum bomb too. You get this overblast, and then you have kind of a vacuum. Think of somebody doing a cannonball in a swimming pool, right? They go under and they push the water out of the way, and then there's a vacuum where they were. And so then that water comes back, and that vacuum effect happens in the atmosphere too with a big explosion. And so those can be devastating to solid, rigid structures like buildings. So you push and then you pull and things fall down. Quite a range of topics today, as you probably didn't expect. All right.